Hello, my name is Hallie, and welcome to this exploration of enthalpy. Enthalpy is one of the three main players of thermodynamics, and it's important that on test day you know how to identify the different types of enthalpy and are able to use it appropriately when making calculations. On test day, it's likely that the exam writers will ask you to find the total enthalpy of a reaction, but they can give you the information or the data for a chemical reaction in a few different forms, such as the standard enthalpy, Hess's law, and bond dissociation energy. And by completing this review, you'll feel more comfortable using each of these data sets, and you'll be able to attack questions such as the one at the bottom of the screen, which asks you to find the total enthalpy for a reaction. Enthalpy is brought to you by the letter H. Why the letter H? Well, because enthalpy represents the changes in heat at a constant pressure. If you think back to your general chemistry laboratories, you might remember an instance where when you were mixing reactants together, you noticed that the reaction flask became either hot or cold, even though the conditions of the room around the flask did not change. And this is an example of the heat content or enthalpy of a reaction changing even though the pressure and temperature of the environment surrounding the flask were kept constant. Enthalpy is a state function, meaning that it doesn't matter how many steps of the reaction need to occur in order to form our products. All we need to do to find the total enthalpy of the reaction is to compare the enthalpy of the final state and subtract out the enthalpy of the initial state. You probably remember from general chemistry that a positive enthalpy value is endothermic, meaning that the reaction wants to absorb heat from its surroundings in order to proceed. So if you did a reaction in a lab and the flask became cold, that was an endothermic reaction. However, if your flask became hot, that was an exothermic reaction, or heat was being released into the surroundings because the reaction had a negative enthalpy. Now, be careful on test day. There's a very common MCAT trap that the exam writers will ask you to deduce the spontaneity of a reaction from the reaction's enthalpy, and you can't do this from enthalpy. You can only determine the spontaneity of a reaction from Gibbs free energy, so be careful. Another tidbit you want to know about enthalpy for test day is the standard enthalpy of formation. Now, this is a standardized number that was determined in a laboratory, and this is the enthalpy required to produce 1 mole of a specific compound from its elements in the standard state. The standard state being 298 degrees Kelvin and 1 atmosphere of pressure. 298 degrees Kelvin is the same as 25 degrees Celsius, or about room temperature. The heat of formation for elements created in the standard state is always 0. For example, oxygen will always be in its gaseous state at this temperature and pressure, sodium as a solid, mercury as a liquid. However, do not assume that a molecule's standard state is the same state that it's commonly found in nature. For example, sodium in nature is usually in its aqueous form. However, for the purposes of standard state, we use sodium in its solid form. The standard heat of reaction is the enthalpy change for a reaction under standard conditions. Again, 298 degrees Kelvin and 1 atmosphere of pressure. This is parallel to our general chemistry laboratory example, where if we were creating products from the mixing of reactants and we had a temperature change of the flask, even though the environment of the room did not change, then there was a standard heat of reaction for that mixture. And to find the enthalpy of that reaction, again, this is a state function, so all we would have to do is to find the sum of the enthalpy of the products, or the final state, and subtract out the sum of the enthalpy of the reactants. And we are only able to calculate the standard enthalpy change for a reaction if we know what the heat of formation for those compounds are. Hess's law really just defines something that we already know about enthalpy. We just haven't put a name to it yet. But Hess's law states that the enthalpy of a reaction is the sum of each step of the reaction. We've already identified that enthalpy is a state function. So to find the total enthalpy of a reaction, look at the difference in enthalpy between the initial and final states. However, Hess's law states that really in a chemical reaction there are several intermediates, and each step of the reaction is going to have its own enthalpy. And some of these steps may be exothermic or endothermic, but we can add all of these enthalpies together to find the total enthalpy of the reaction. And Hess's law is not exclusive to just enthalpy. It really applies to all of the state functions, including entropy and Gibbs free energy. We've already identified that on test day, you may have to find the total enthalpy of a reaction by using either the standard heat of reaction or Hess's law. Bond dissociation energy is the third and final way that you may be asked to find the total enthalpy of a reaction. The bond dissociation energy is the amount of energy required to break a bond, and since we're dealing with energy, we would expect the units to be in joules, in this case in kilojoules per moles of the bonds that need to be broken. And since bonds require an investment of energy, usually given in the form of heat, we consider these reactions to be endothermic. If we know the bond dissociation energy for a reaction, we can find the total enthalpy of that reaction. And all we would have to do is take the total enthalpy of the bonds broken and subtract out the total enthalpy of the bonds formed. Now, remember, bonds broken actually represents your reactants and bonds formed represents your products. So this enthalpy equation actually breaks the trend of all other enthalpy equations we've looked at so far, where we're actually taking the initial state minus the final state. But look at this from a thermodynamics standpoint. Bonds broken represents endothermic reaction. So we'd expect that enthalpy to be positive. And then bonds formed is exothermic. So we would expect to subtract that enthalpy from the enthalpy of the bonds broken. You could also look at this as the enthalpy of the reaction is going to be the total energy absorbed minus the total energy released. By test day, you will want to be comfortable using the bond dissociation energies to find the total enthalpy of a reaction by using the equation listed here. Because this equation is going to help you to solve for one of the MCAT's favorite general chemistry questions, finding the amount of energy that will be released when a fuel is combusted. In nature, there are many ways to combust a molecule, but the MCAT will only present you with one type of combustion reaction, and that is when we burn a hydrocarbon in the presence of oxygen to release carbon dioxide and water, such as the combustion of propane. We expect the enthalpy value for these reactions to be large negative values because we know when we burn a fuel, we release heat. And we would expect these to be exothermic, but be careful when doing your calculations. Make sure that your equations are balanced prior to starting any math because more than likely the MCAT will not balance these equations for you. Since finding the heat of combustion is a common question on test day, let's work through one example question together, such as the burning of methane. Remember, we want to plug our bond dissociation energies into this equation in order to find the total enthalpy of the reaction. But before we do any math, we need to make sure that our equation is balanced. It looks like our carbon atoms are balanced, but we have 4 hydrogens on the left and only 2 on the right, so let's work with 2 moles of water. And looking at our oxygens, we have 2 on the left but 4 on the right, so let's add a 2 in front of our oxygen. So now we're ready to start plugging into our enthalpy equation. Let's start with the bonds broken, such as methane. We're given the bond dissociation for a single carbon-hydrogen bond, but for every mole of methane, we're actually going to have to break 4 carbon and hydrogen bonds. So we're going to multiply this bond dissociation energy by 4. We're also going to break the bonds on oxygen. We were given the oxygen bond dissociation as 2 oxygen molecules double bonded together, but we're working with 2 moles of oxygen, so we will need to multiply this by 2. Now looking at the bonds formed, or the exothermic half of our reaction, we are given the carbon-oxygen bond dissociation energy as a double bond. However, we are working with carbon dioxide, not carbon monoxide, so we do need to multiply this by 2 as well. And we are working with 2 moles of water, and we have to break 2 oxygen and hydrogen bonds per mole of water. So we need to multiply this by 4. Now we can start plugging in the values. Remember, the MCAT is a test of how well you can use the information provided, not of mathematics. So we will have enough wiggle room between our answer choices so that we can round our bond dissociation energies to numbers that are easier to work with. For example, the CH bonds can be rounded to 400, oxygen double bond to 500, the carbon-oxygen double bond to 750, and the oxygen-hydrogen single bond to about 450. At this point, this is a simple plug and chug, and we find that the total enthalpy of our reaction is going to be somewhere around negative 700 kilojoules per mole, which is what we would predict since this is a combustion and we will be releasing heat into the universe. And when looking at our answer choices, we find that the actual answer is negative 656 kilojoules per mole. Now that we have had some practice finding the standard heat of combustion, let's find the total enthalpy of a reaction when given the heats of formation. Remember that using bond dissociation energies to find the total enthalpy of a combustion reaction breaks the trend of all other enthalpy formulas. To find the total enthalpy of a reaction when using the heats of formation, we need to take the total enthalpy of the final state minus the total enthalpy of the initial state. And once we set up our equation, we can start plugging in values. Remember that it is perfectly acceptable to round these numbers either up or down in order to make them easier to work with. And hydrogen, in its elemental gaseous state, or its standard state, will have a heat of formation of 0. And we find that the enthalpy of this reaction is about 60 kilojoules per mole, which is very close to answer choice C. Let's try this question, which asks us to compare the bond enthalpy of diatomic hydrogen to the heat of formation for this molecule. And the correct answer is B. Remember that the heat of formation for any molecule in its standard state is always set to 0. So this value is arbitrary. It simply gives us a good starting place to observe the changes in enthalpy as this molecule moves away from its standard state. Roman numerals 1 and 3 may present true information, but this doesn't contribute to the bond enthalpy holding the diatomic hydrogen together. So what do we really need to know about enthalpy for test day? Well, the value of enthalpy, whether it's positive or negative, can tell you whether a reaction is going to be endothermic or exothermic. And the standard heat of formation is the enthalpy required to create 1 mole of a compound under standard conditions, while the standard heat of reaction is the change of enthalpy between its final state and the initial state. Hess's law states that although we look at enthalpy as a state function, it really can be a sum of all the parts of the reaction. Bond dissociation energy is the sum of the enthalpy of the bonds broken minus the bonds formed, and the standard heat of combustion is the enthalpy that will be released when a hydrocarbon is burned in the presence of oxygen, for the purposes of the MCAT anyway. Well, that's what the exam writers expect you to know about enthalpy for test day. Hopefully you now feel more comfortable about how to define the different types of enthalpy and how to use these values when making calculations. Thank you for joining me, and as always, best of luck on that exam.